Okay, here's section 12.5, square roots of variable expressions. So let's take a look. Earlier in chapter 12, we were just simplifying square roots of numbers. So if we were to simplify the square root of 8, okay, how we would do it, simplifying by factoring, would be we would get the square root of 2 times 2 times 2. So let's see what that would look like. Don't cheat. Okay, so we would have the square root of 2 times 2 times 2, which we know would simplify to 2 root 2, because we were looking for pairs of 2's there, because we know we could pull one of those 2's out. So it's the same thing with variable expressions. So if we're looking at, say, the square root of x squared, that's really the square root of x times x, which would just be x. So it works the same way with variables. So the square root of x cubed, there's one pair of x's that we could pull out, so it would be x root x. X to the fourth, there's two pairs of x's to pull out, so it's x squared. And the same thing would happen with x to the fifth, x to the sixth, x to the seventh, so on and so forth. So you're just looking for how many pairs of x's can you pull out. So a little shortcut that we talked about in class is you just take the exponent and divide it by 2. So for example, x to the fifth, 5 divided by 2 is 2, so you know you can take out an x squared, and then there's a remainder of 1, so there's just one x left underneath the square root. So that'll work for any of them. We also talked about in class how the square root of x squared isn't actually just x, it's the absolute value of x. Okay, this is the only one that I need you guys to know for right now. And the reason that it's the absolute value of x is because we don't know the original sign of x. It could be a positive or a negative number, but we know that if we had the square root of negative 2 squared, we're really just taking the square root of 4, which is positive 2. So that's why we need these absolute value bars here, because we always want it to be positive. Okay, so try simplifying these next few and then come back for the solutions. Okay, so the square root of 14x to the 8th, the square root of 14, you can't simplify that anymore because it's just 2 times 7, so there's no doubles there, so that stays the square root of 14. But the square root of 8 is x to the 4th, so the answer would be x to the 4th times the square root of 14. Over here we have the square root of 27, x to the 5th. Now if I just look at the square root of 27, I know that it's 3 times the square root of 3, because 27 is really 9 times 3, so the square root of 9 would give me that 3, that's why I could pull that out. And now then I look at the square root of x to the 5th. I know 5 divided by 2 would be 2 with a remainder of 1, so the square root of x to the 5th would be x squared root x, so this is what I end up with. Okay, now here I have the square root of 45, x cubed y to the 4th. I broke down 45 as 9 times 5, so I know the square root of 9 is 3, so that's why I pulled that 3 out right there, and then I left the 5 underneath the square root. The square root of x cubed is x root x, and the square root of y to the 4th would be y squared. So I have 3xy squared times the root of 5x. And then here, square root of 25x to the 6th, y to the 11th. I know the square root of 25 is 5, so I pull a 5 out, and then the square root of x to the 6th would be, there's 3 pairs of x's there, so it would be x cubed. And then the square root of y to the 11th, there's 5 pairs of y's there, so it would be y to the 5th times the root of y. Okay, now try these next 4 examples and then come back for the solutions. And remember, when you do these, you need to make sure there's no square roots in the denominator and that everything is completely simplified. Okay, so for here, the first one, I notice that there's a square root of y in the denominator, so the first thing that I want to do is multiply the numerator and the denominator by the square root of y so that I can get rid of that. Oh, actually, I didn't do that first. Let's see what I did. Actually, first, I noticed that I could actually cancel out that square root of y in the denominator. So I broke the square roots in the denominator up as root of x times the square root of y to the fifth at first, so let's get rid of that. Right. So that's what I did first, is I just broke up the square root in the numerator. And then I know that if I the square root of y to the fifth divided by the square root of y, I know that one of the square roots of y's will cancel with the top and the bottom. So I would have the square root of y to the fourth left over in the numerator. So this is what I have. I have the square root of x times the square root of y to the fourth over 1 now. The square root of x I can leave as the square root of x because I can't simplify that anymore. The square root of y to the fourth is y squared, so that's my final answer. In the second one, though, with the square root of b in the denominator, there wasn't any square roots of b in the numerator for me to cancel that out, so I did have to go through and rationalize the denominator. So I multiplied by the square root of b over the square root of b. So in the denominator, root b times root b is b, and then I have the square root of a to the eighth times b. If I look at a to the eighth, the square root of a to the eighth is a to the fourth, and then the square root of b just stays the square root of b. So my final answer would be a to the fourth root b over b. Here, the first thing I did was I rewrote the two roots as all one square root. So I have the square root of 6 times 15 times x squared times x cubed times y. Then I looked at 6 and I said, well, 6 is really 2 times 3, 15 is really 3 times 5. And then x squared times x cubed is really x to the fifth, and then y just stays y. So if I look at the numbers, I know there's a double 3, so I can pull out a 3, and then I'm left with the square root of 10 underneath. And then the square root of x to the fifth is x squared times the root of x, so x squared goes on the outside, x stays on the inside, and then the y stays where it is. So that would be my simplified answer. All right, the next thing, so let's get rid of these little marks for now so that I can show you what I did first. Okay, so the first thing I did was I broke down the root of 14 as the root of 2 times 7 and then left x cubed there. And then for the denominator, I rewrote it as 10 times the square root of 3 times 7 times x to the 7th. Because now I can go through and I can cancel out the square root of 7 with the square root of 7, and then the square root of x cubed with the square root of x cubed. So if I take away x cubed from that, I have left the square root of x to the fourth in the denominator. Okay. And then also I notice that 4/10 I can simplify that to 2/5. So what I have left here after I cancel out from the beginning is 2 root 2 divided by 5 times the square root of 3x to the fourth. I know that I can simplify x to the square root of x to the fourth as x squared, so I just rewrote it as 3x squared times the square root of 3 in the denominator. Now I just have to get rid of the square root of 3 in the denominator, so I multiplied the top and bottom by root 3. So I end up with 2 root 6 divided by 3 times 3, which is 9, x squared. And I cannot simplify that anymore because there's no variables in the numerator and the denominator to cancel. The constants don't simplify anymore, and everything underneath my square root is completely simplified. Okay, here's the next thing. We have to simplify x. You know what, try these first, and then I'll come back and give you the answers. Okay, so we have to simplify the square root of x plus 4 times the square root of x minus 3. So I just rewrote it under all one square root so I can see what I'm kind of working with. So we have the square root of x plus 4 times x minus 3. They're not repeated factors, so x plus 4 is not the same as x minus 3, so we can't take the square root of that. So there's nothing more we can do other than just make sure everything is completely simplified underneath the square root. So that means we actually have to go through and simplify x plus 4 times x minus 3. So when you multiply that out, you would get x squared minus x plus 12. And remember, you can use that box method, the area model, to help you multiply it out if you can't do it in your head right away. So this would be our final answer because there's nothing more that you can do. So here, the second problem, the square root of x minus 10 squared. So what I did in red here is kind of make myself a little note. Like, let's make it a simpler problem to think about. If we just had the square root of x squared, right? That's all we're doing, is we're taking the square root of something squared. We know that it's the absolute value of x. So the same thing applies here. So the square root of the expression x minus 10 squared would just be that expression, x minus 10, but remember, don't forget the absolute value bars. This third one here, the square root of x squared plus 12x plus 36. If you look at this trinomial, it is a trinomial square, so you can factor it into a binomial squared. So you want to factor that. So it's x plus 6 squared. And you can take the square root of x plus 6 squared because that's just the absolute value of x plus 6. Right, just like we did in this first one. So the key here is when you start off with a trinomial, you want to factor it to see if you get repeated factors that you can then take the square root of. All right, this last one, we have the square root of x plus 6 to the 5th power. So again, in red here, I just thought, okay, let's make it a simpler problem. I know that the square root of x to the 5th is x squared root x because I have I have two doubles of x's underneath the root here. So it's x squared with one x left over. So the same thing applies here. The square root of x plus 6 to the 5th, I could pull out two factors of x plus 6, so it's x plus 6 squared, and then I'm left over with 1 x plus 6 underneath the square root. So this would be my final answer.